2. And if I want to make it even more clear, I would say z greater than 1.23. 1.23. So we would go to 1.23 on your z curve. No matter what z curve you're using, there are two there. There are two z's and two t's there, right? So I go to 1.2, and then this 3 is the hundredths place, and the 1.2 was taken care of here. So when I go to the intersection of 1.2 row and 03 column, I get 0.8907. Now mind you, 1.23 is here. 8907 is this area, but that's not the part I want. I want this, because it says greater than. Now, if it said greater than or equal to, I would do exactly the same thing, because as we said last time, there is no area at the point 1.23. So whether you include it or whether you exclude it, it doesn't matter. So I go here, 1 minus 0.8907. That's your answer. So you stick that in your calculator, and whatever you get, you get. Follow me? Yeah.
Can you explain again why it's 1 minus 0.8907?
Yes. The total area under this curve is 1. Under any continuous curve. Okay? So if this is a PDF, probability density function, then the total area is 1. Now, the table gives you phi of z. So if this is z, you look up the table, it gives you phi of z. Right? That's the cumulative distribution function. Remember that from calculus? It's the area to the left of what you look up. Since it's talking about z, this is the z curve. This is the number for z that you're going to look up. So let's say you look up z equals 1. So phi of 1 will give you the area to the left of 1. So what is the area to the left of 1? Can you go look it up on your table? It should be 0.8413, right? I already know it's going to be 0.84 because it's empirical rule, remember? And empirical rule tells me this is 50%, this is half of 68, which is 34. So I know that I'm expecting 0.84 here. So 8413 gives me a feeling of, yes, this is a good thing. I'm in the right place, right? So this is 0.8413. And if I'm looking for probability z greater than 1, then I would be looking for that. And that would be 1 minus 0.8413. Does that make sense? Yeah? Okay. What about probability z less than minus 1? Probability z less than minus 1. So I'm here at minus 1, and I'm interested in this area. What do you think? Yeah.
0.1587.
Yes, 0.1587 from looking up the minus part of the table, right? Now, this answer is the same as that answer. Not surprisingly, right? Look at this. I'm talking about this versus that, and this is the z curve. So, of course, there's symmetry, so I expect this answer to be the same as that, and they are 1.1587 in each case. Are you with me or no? Speak up if you're not. And then the other thing we mentioned the other day was that if you're looking for the area between A and B, then this would be phi of B minus phi of A. Phi meaning table lookup. Phi of B minus phi of A. So if I want the area between minus 1 and 2, can you find it for me right now, please? So I'm interested in probability z between minus 1 and 2. And just to make it interesting, I'm going to add an equal to sign here. But you already know that that's meaningless, right? Yes? Okay, go do it. For every one of these problems, I would prefer that you draw a z-curve, because when you make a mistake, your brain will signal you into the fact that there's a mistake, because look at what this looks like. -1 to 2. So if you got an answer of 0.44, when all was said and done, something's very wrong, because you see how much area there is here, right? So to this day, even years and years and years later, I'm still drawing the curve so that the visual has to match the answer. Now this will be the last part of your problem that you do. So the problem will be much more complicated. This will be the last step that you do. Okay? So if you don't have your table, here's the table. Phi of 2, that's right here, 0.9772. We talked about that number last time, right? We were expecting 97.5 percentile, right, at 2 standard deviations to the right of the mean. And this one is saying 97.72, so I'm pretty close. So phi of 2 minus phi of -1. 0.9772 minus phi of -1 was 0.1587. We just did that. So you do this and that's your answer. It's this minus that. Get it? Okay, so let's move on. So all these problems on page 4 and 5 are now doable by you. There should be no issue. Okay? So let me go to page 6. I want to start on page 6. From here. Let x be normal with mean 50 and sigma 5. So mean 50 and sigma is 5. So I know that if I go 5 and 5 and 5, I will be at 65. Find the probability that x is greater than 58.5. So I'm here. This is 60. 58.5 is here. I'm looking for this area. 58.5 is this number. Agree? So I don't have a table for this strange function with mean 50 and sigma 5. So of course I'm going to convert it to z using the formula that I know. So probability x greater than 58.5 is equal to probability z. Remember the formula for z is x minus mu over sigma. So I'm going to go here and plug in my x minus mu over sigma. So 58.5 minus the mean. The mean is 50 and the sigma is 5. Agree? So this is probability z greater than 8.5 over 5, which is 1.7. Probability z greater than 1.7. So then you go to 1.7 on your z curve. So if I draw this z, this one was x before. This one is z. Z has a mean of 0, which translates to x equals 50. and 1.7 is somewhere here. So this area and this area have to be equal. This is 1.7. So I'm able to now go to my z table and look up 1.70, which is 0.9554. I'm here. 0.9554. That's this part. I don't want that part. I want this part because it said x greater than, meaning the area to the right. So this would be 1 minus 0.9554. So 0.0446. Make sense? Let's do the next one. Page 6 again. Second example. Let x be normal with mean 10 and sigma equals 2. Find the probability that 8.5 is less than x is less than 12. Same thing. Let's convert them both to z's. Probability 8.5 minus the mean divided by sigma. Less than z, less than 12 minus the mean divided by sigma. So it's probability minus 1.5 divided by 2 is 3/4, so minus 0.75, less than z, less than 2/2 is 1. Let's draw a picture. Z. Notice that I don't even bother to draw the picture for x. It's not necessary, right? It's going to all depend on the z anyway. So if you're going to draw one picture, let it be the z. So z between minus 0.75 and 1. So let's go look up 1. We already know it's 0.8413, or you can look it up. And then let's go look up minus 0.75, which is minus 0.7, and the 05 column gives me 0.2266. 0.2266. And subtract and get your answer. Follow me? Okay. What's your question? Is there a question? I want to draw your attention to one fact. Sometimes they will say x is normal with mean 10 and sigma 2, and other times they're going to say x is normal 10, 4. So if they just give you two numbers, it's your job to understand that the first number is mu and the second number is sigma squared. Variance. The second number is automatically the variance unless they already take the square root and then give it to you as they did here. So you want to keep that in mind, because on your test, for example, it might say something like x is normal 100, 16. This is sigma squared. So all your calculations will have to use sigma equals 4, not sigma equals 16. If you use 16, it's all finished, right? Everything will be wrong. So just keep that in the back of your mind for every problem. Okay, so something like this now, this next example is nothing new. You can do it, right? Just be careful, because this is sigma squared, so your sigma is rad 5. Follow me? There's nothing new for me to teach you here, so I think we should go to the next page. Agree? What I could teach you is how to do it on your calculator. so you can start checking every problem that you do. Let's do one of these on the calculator. How about this one on the calculator? Let me grab mine. So you would go to second function, which is right. I'm sorry, I'm just trying to get it so that it doesn't reflect. Second function, and then the VARS key, which is here, right there. That will bring you to distributions. You're looking for norm CDF. Norm CDF. So go to the second one down. So second, distributions, meaning second VARS, which brings you to distributions. And then you pick norm CDF. The norm CDF left, right, mu, sigma. So the left endpoint is 8.5. The right endpoint is 12. Mu is 10. And sigma is? What's sigma? 2. Right. So here is where you have to be careful, right? So yeah, the calculator will do it, but you better give the calculator the right input. So left, right, mu, sigma. Stick it in and let's see what happens. So norm CDF, enter. And then left endpoint 8.5, right endpoint 12. Mu is 10. Sorry, mu was 100, right? I'm sorry, there's two different problems here. There's this problem, which I'm not doing right now. I am doing that problem up here. So mu is 10 and sigma is 2. .6147. And the answer we got would have been 0.8413 minus 0.2266, which gives me 0.6147 also. Yeah? Are you good? Okay. Next question on page 7. What if it's greater than? So let's do a problem like that. Yeah, I'll do it on the calculator. So let's say the question says x is normal with mean 90 and comma 3. Find the probability that x is greater than 91.2. Let's do it on the calculator. Norm CDF, left 91.2, because I want the area to the right of 91.2, right? So the left endpoint is 91.2, comma, right. Right endpoint will just be infinity. So put in any big number that you want. This is infinity. Left, right. So how about 1,000? That will certainly take care of it. I don't have to do any thinking there. Comma, mu. Mu is 90. Comma, sigma. What's sigma? Rad 3, exactly. That's it. Done. Similarly, to the left side, you would go to minus infinity. So let's say the question was, find the probability that x is less than 88.9. Let's say that's the question. I'm going to do norm CDF. Left endpoint minus infinity. Right endpoint 88.9. Mu is 90. Sigma is rad 3. Follow me? So putting something here like a 0 would be okay also. And putting something negative would be fine too. Because you look at this curve for a minute. If I have a curve like this with a mean of 90 and a sigma equals rad 3, which is 1.732, I know that going a 1.7, a 1.7, and a 1.7 will bring me to the end of my curve. So whether I put minus infinity here, or minus 5 here, or 0 here, all those would give me the same answer, right? Because there is nothing past 3 standard deviations to the left of the mean, pretty much. Follow me? Okay. Let's do the next one. I'm on page 7. If x is normal with mean 25.7 and variance equals 5.88, so here x is normal, 25.7, I don't even have to write variance equals because it's understood that this is the variance. What is the minimum x required to be in the top 10% of the distribution? So this is my x. This is 25.7. And I'm interested in what is this number such that this area is 10%. How do you think I should go about this problem? Any ideas? Yeah.
Maybe go in the Z table and look at which values is like 0.9.
Yes. So if this is 0.1, I'm really interested in the area to the left side because that's what the Z table deals with, the phi of Z number, right? So this is the 0.9000 number. And I'm going to look at my table and come as close as I can to 0.90. So it's on the right side, on the positive side of the Z because I'm on the right side here. And I would imagine 0.8997 is as close as I can get. Look over here. 8997 corresponds to 1.28. And the other one, the one that's larger than 0.9 would be 0.9015. 0.9015 is further away from 0.9 than is 0.8997. So I'll go with 0.8997. So I'm dealing with 0.8997 is as close as I can come, and this would be Z equals 1.28. But unfortunately here I'm talking about X and not Z. So first I would have to write it like this. 0.8997. This is a Z curve, 1.28. And what is the X that corresponds to that Z? You see where I'm going with this? The curve gives me the Z value, but I want the X value for some strange curve with a strange mean of 25.7, right? So 1.28, that's the Z, equals X minus mu over sigma. X is what the number that I'm looking for. Mu is 25.7, and sigma is rad of 5.88. Are you with me or not? So let's solve. 1.28 times rad 5.88 plus 25.7 equals X. Everybody okay? So what do we get? 1.28 times radical 5.88 plus 25.7. 28.8038. 28.8038 equals x. So this unknown value that I was looking for here is 28.8038, and that's my answer. Is this the best way to do this problem? The answer is absolutely not. Okay, let me show you the most efficient way to do this problem other than the calculator, all right? So there is some other table that I had asked you to print out for today, and that's called the t-table. If you could pull that one out, I want to show you how you would use that t-table. So first of all, the t-table doesn't work like the z-table. It works differently than the z-table. The t-table deals with the area in the tail, whereas the z gives you the area to the left of what you look up. The t doesn't work that way. The t will deal with this area in the tail of the distribution. And these numbers up here correspond to what's in the tail of that distribution. So I could have just done this, gone to 0.10 and gone all the way down to the last row, because the limiting case of the t distribution is the z distribution. Let me explain that a little better, okay? This deals with a distribution that is the student's t distribution, which was discovered by William Gossett. And William Gossett worked for a brewery that frowned on any kind of independent research. So he published all his research not under the name of Gossett's t distribution, but he had to publish all his research, all his findings under the pseudonym student. That's why it's called the student's t distribution. And what this is the limit. So z is the limit as n approaches infinity of the t curve. So the t curve is based on the number of degrees of freedom, n minus 1. You remember that from the exam 1 material, the Bessel's correction, n minus 1? So these numbers in the margin of the t distribution are n minus 1 degrees of freedom when you're talking about the t curve. And it says here degrees of freedom. So you know. So what I'm trying to say is when your degrees of freedom reach infinity, the t approaches the z. So if I were to draw a bunch of curves, and I might even have drawn them here for you in your notes, I'm pretty sure it might be in a different chapter that I did them when we actually, it's later on. But let me draw a picture to show you. So if this is z, this would be a t curve. Very, very similar, symmetrical, unimodal. So these t's have thicker tails than z. So these t's will approach z as n goes to infinity, and therefore, for our purposes right now, we can just go to the last row of this t-table and cheat and pick up the number that we need, because as we know, this t deals with the area in the tail. So if I'm looking for 0.10 in the tail for z, all I have to do is go to my t-table and look up the 0.10 column and go all the way down, because I'm interested in z right now, not a t curve. I'm not interested in t with 9 degrees of freedom because n is 10, because I'm not talking about that. I'm interested in t with infinite degrees of freedom. So I went to the last row, and I will pick up this number that I see under the 0.10 column, this 0.10 column right here. So I see 1.282. That's the exact number. And then I would do exactly what I did before. So 1.282 equals x minus mu over sigma. Well, this is given and this is given. This is the unknown. And you cross multiply and you solve just like we did before. Follow me? So how do you do this on the calculator? I'm sorry, you had a question before.
I was just gonna tell you to zoom out. You couldn't see.
Zoom out?
Yeah. That's good.
That's better for me too because I can fit more to a page. Any question on this? How do you do this on the calculator? Second, VARs. That'll bring you to distributions. And then inverse norm. Inverse norm. And the argument of the inverse norm is the percentile. You have to be careful here because when you're looking for 10% in the right tail, you're looking for P90. Right? So even though you have the use of this calculator, you constantly have to be focused on whether you're putting in the right stuff. Because if you put in inverse norm 0.1, it's going to give you something to the left side of the mean because that will be giving you the stuff in the left tail with 10%. Meaning, if you put in inverse norm 0.1, it's going to give you this number. And you don't want that number. You want P90, not P10. So inverse norm, percentile, which is 0.9, comma, mu, comma, sigma. So since we have an answer to this problem on the previous page, why don't we go and do it on the calculator and see if it comes close? So, second, distributions, inverse norm, which is the third one. So you go put in the percentile, which we said was 90%, 0.9, comma, mu. Mu was 25.7, and sigma was rad 5.88. 28.8075. Close enough. And of course, this was done with 1.28, not with 1.282. Had I used 1.282, I would have gotten a better number, right? So let's see. If we put in 1.282 here instead of 1.28, what do we get? 1.282 times rad 5.88 plus 25.7. 28.8087. And the real answer, the exact answer, is 28.808. Also here I have 28.809. So it differs by 1/1000th, which is not much. Get it? So what's the difference between norm CDF and inverse norm? Norm CDF gives you area when you input the Z or the X. Let's write this. When you have X going from A to B and you're looking for the area, that's when you do norm CDF. Left, right, mu, sigma. So your left would be A and your right would be B. And your mu and sigma would be given. And on the other hand, when they give you the area and you're looking for the X, you would do inverse norm. So let's say they say, find the cutoff. Let's say I want to fail 12% of my class. Usually we fail like 3% of the class or something, very low percentage. But suppose I wanted some cutoff for 12%, the bottom 12%. So let's say you're failing 12% of some class, and the mean is 70, and the sigma is 3.8. Please find the cutoff for failure. That's the question. So first of all, when I go to look this up on my t-table, 0.12 is not there, so I can't do this by hand. I have to use the calculator, right? You would be stuck without the calculator. So you would go inverse norm Since they're giving me area and I'm looking for the x, it has to be inverse norm. Percentile. So percentile is 12%, comma, mu, comma, sigma. Just like that. Get it? What did you get when you did that?
69.535.
Let's see. Second distribution, inverse norm, 0.12, comma, mu, 70, sigma, 3.8. 65.54, yeah? That's my x. Any issues? Yeah.
How do you know, 0.12, that's the area?
Because I want to fail 12% of my class, that 12% is going to be in the lower tail rather than the upper tail, because look where 12% in the upper tail would lie. So this would be close to an A minus, not a failure, right? Because that's in the top half. So this one, if I was looking for this number, it would be inverse norm. What do you think it would be, guys? Yeah. Percentile is 88, comma, mu, comma, sigma. Now, what if you don't put in the mu and the sigma? What happens? Go do it on your calculator and see what happens. What if you do inverse norm 0.88 and you don't put in the mu and the sigma? What do you get? 1.17 for what? 49. What do you think this is? So if you don't provide mu and sigma, it assumes that you're talking about the z curve. So it's saying on the z, if this is 0.88, then this would be 1.7, I sure it said 1.17? What did you get when you did it, guys?
I didn't get anything.
Second distribution, inverse norm, 0.88. 1.1749. So you're right. 1.1749. It makes sense, right? Because one standard deviation to the right of the mean is 84th percentile. So this is slightly more than one standard deviation of the mean. The standard deviation is 1 in the case of z, right? So the answer makes sense. So if you don't put in the mu and the sigma, it assumes you're talking about z. It assumes that the mean is 0 and the sigma is 1. Good? Yeah.
So if you want, like, the uppermost percentage, say like 95, then you would put in something like 0.05.
No, if you want the upper 95, you would put in 0.95. Because, I mean, if you want the upper 5th percent, is that what you're talking about?
Yeah.
This is 0.95. The percentile is P95. So this would be inverse norm, 0.95, comma, mu, comma, sigma.
Let's say you wanted like the lowest 5%, then you would do 0.05.
Yes.
Okay.
Yeah. Good? Okay. So let's get back to the text, the typed.
Wait, if you wanted, so if you're still doing that example, would you just subtract to get the 0.95? That doesn't make sense.
Subtract from what?
So you said that we have to use the 95th percentile, right? To find the 0.05 area.
Mm.
Will we just subtract to find the area of 0.95?
Where do you want the 0.95 to go?
So
Here.
like how do we,
Suppose this is my curve. Where do you want to go? Where do you want me to draw the line?
so like the same way that we have it there, so the
Mhm.
95th percentile.
Mm-hmm.
So, dang. Actually, never mind.
Do you mean this? Are you saying that will this be the negative of this value?
Yeah.
It won't.
Okay.
It will be the negative in the terms of z,
Okay.
but when you convert it in terms of x, you can't just negate it, because the mean here will be some strange mean, right?
Mhm.
So let's say the mean is 20, and let's say that you have some value right here for the 95th percentile. This will be symmetric about 20. So
Okay.
you can't just take the negation of this and put it here. You can on the z. In the case of z, you can. If this is z, you can say this is 0.1 and this is 1.282, and therefore this is minus 1.282, and this is 0.1,
Okay.
right? But once you convert it to x, that doesn't work, because this x is symmetric about 20, not about 0. So you have to be careful there. Okay, so z.10. So I'm back to the notes on page 7. It says, let z alpha denote the value of z such that the area under the standard normal curve to the right of z is alpha. So it's so many words, but really, if you just look at this picture, here's my alpha. Alpha. If this is alpha, this is called z alpha. So if this is my alpha, this is z alpha. Z alpha is the value of z such that alpha is the area in the right tail past that number. So let's just practice a couple. What is z.05? That means 0.05 is in the right tail. It's always in the right tail, okay? The upper tail. So this number is z.05. So simply go to your T table and look up 0.05. I'm going to the T table because that deals with area in the right tail. So 0.05, and go all the way down. All the way down in the 0.05 column, I see 1.645. So this number is 1.645. The negation of it would be minus z alpha, and that would be minus 1.645. Here's 0. This is z. So z alpha is on the right side of 0, because 0.05 is the area in the tail on the right side. Follow me? So this is like your alphabet right now. We're going to start using these z alphas and z alpha over 2 very freely. So you make sure that you understand that when alpha is in the right tail, z alpha is the cutoff on the right side. Get it? No?
Wait, can you say that again?
Yeah. If alpha is the area in the right tail, z alpha is the cutoff providing that area in the right tail. So let's say I was looking for z.025. Let's say that alpha is 0.025 and I'm looking for z.025. That means go to the T table, go look up 0.025 in the T table. 025 column, last row, 1.96. So this is 1.96, where 0 is here. Get it? And on the left side, automatically, notice that this T table doesn't have any minus stuff going on, right? So it's up to me. It's symmetric, so it's up to me to say if this is 1.96, then this is minus 1.96. Because it's symmetric about the mean of 0 if I'm talking about z. If I'm talking about x, it's symmetric about the mean mu. Follow? So I'm going to start throwing around these z alphas and such, and it doesn't mean, it's not that hard. It's just saying, go to your curve, put alpha in the right tail, and I'm talking about this number, that's all.